Instead of a programming contest today, I'm going to show you how I wrote some computer code to play a game better than I can. This is Dungeons and Puzzles. It's a puzzle game. It's on Steam. You can pick it up for like $8 if you want. And so what's the idea? So we have this character. Right? This is like a tutorial level moving around. You can pick up some items on the ground. There's 4 different items. Right, so you can see the sword shows up here. And the goal of each level is to kill all the monsters, which opens the door. And then we want to get through the door down to the stairs. And so every level has like a par number of moves. In this case, it's 7. And so in addition to completing levels, you should try and complete them as fast as possible. So in this case, 7 is the best you can do. In other cases, it is possible to get below par. Okay, so that was the sword. That's like the first tool. There's 4 different tools in this game. So here's the bow, and we also have the portal. Right? So portal, you just teleport between the 2 portals when you walk on it. There's also this stool, which stops your movement. Right? Normally, you can't like stop moving until you hit a wall, but when you're on a stool, you stop. And then there's the bow, right? So you can shoot an arrow at range. And then once you shot an arrow, the bow is now empty. You can't shoot again. And the arrow is on the ground, but you can go pick it up and shoot it. So we can go like through this portal, shoot this guy. I messed up this level because I need to shoot this guy last so that I can actually get to the door. Right? Because the way that I did it, I didn't really have a way to get to the door. I could just go around this little rectangle. So there's the puzzle part, I guess. But if I shoot the other guy first, then I can solve this level in a par number of moves. Very nice. Okay, so that was the bow. Another tool is the shield, which lets you push stuff around. So including stools. Notice that if I walk, I land on the stool. If I push, the stool moves and I land before it. I can push this enemy around. Let's see. I can push this obstacle around, shove the enemy into the spikes, which kills him. Notice there's no like sword or bow on this level, so the only way to kill the enemies is to push them into the spikes. That completes this level over par, but you know, that's okay. I'm just trying to show you how the game works. This level introduces the last tool, which is the glove. So the glove lets you pull things, like the shield is push, the glove is pull. So I can, and also notice this enemy is big, it takes up 2x2 squares. So I can pull him into the spikes and then go through the door. Okay, so that's like most of the sort of elements of the game, quickly introduced. Right, the main thing is these 4 tools, and then there's also like portals and stools, and there's movable obstacles, and of course the enemies, which are basically either 1x1 or 2x2. Okay, so let me show you the program that I wrote. So this takes the level in a text format, which I sort of manually transcribed. So if you look at this level, you can see, you know, this is basically the playable area, and there's the sword on the ground, and the character, and the monster, and the door. And so, you know, in text, there's the door, and the monster, and the sword, and my character. And if I run my program, it will think for a second, and then it will say, okay, you can win in 7 moves by moving up, right, up, left, and then use the sword on the monster. Right, that's what the 2 means. So use the sword to the left, and then left and up. Okay, so the program could be up that level. You know, that's a pretty easy level. Let's try this bow level that we were looking at before. That's 17. Oh, did I not write that one down? Okay. Let's look at a harder level. There's 150 levels in this game, so we'll go down near the bottom, 131. So you can see the level's not like super big, but we have 3 of the tools, and also it's going to take some work to get to the sword with just these 2 tools, and you know, par is like 40 moves. So what happens if we throw this into the program? So I was thinking a bit. I'll explain maybe what that output is later, but eventually it says, okay, not too long. It says 32 moves, and here they are. So let's execute them. So right, and then up, and then 5 down, right, drag the guy with the glove, left, up, push, pull down with the glove, right, up, 5 left, pull with the glove, 4 up, 4 down, shoving everything away from me, 1 down, 1 right, 5 left, 5 left, and now let's see, I'm on move 17, 4 up, 1 right, 5 up, 5 left, 1 down, 1 right, 1 up. Okay, so we can see that it finally got the sword. That'll be useful. 1 down, 2 down, left, up, 4 right. Okay, and you can pretty much see what it wants to do now. Just gonna go up here, kill everything, and finish the level. In 11 under par, which is pretty good. Cool, so that's sort of the program in action. So let's talk about how it worked. So this is basically, the algorithmic part of this is actually very simple. It's just doing breadth first search. Right, so we have some start state, and then we have some queue of things to explore. So grab a start state. If we finish the level, then print out the moves. Otherwise, for every legal move we can make, right, legal move brings us to a new state. If we haven't seen that state already, mark down how we got to that state. Right? It was from our state X with its given move, produce the state Y, and then add this new state to the queue. So that's like very standard BFS. I guess the only thing that's a little bit complicated is I actually want to be able to show the path at the end. So I keep track of sort of the BFS tree of where we came from. Right, so this is saying, how did I get to this state? I got to it from this state by making this move. I'll explain what a state and a move are in a bit. And then to show the path, right, from some end state, you just keep looking back in this directory of how you got to various states until eventually, if you keep going backwards, you eventually get to the start. And then you can print out all those moves that you need, which is how you got there. In reverse order, right? Because we generated, we went backwards from the end to the start. So that is sort of the algorithmic part of the story, right? Very simple, as I said. The tricky thing here is implementing all of this, right? You can see, this is line 450 of this file, and all of this part that I said was the whole algorithm, right? That's like 50 lines, and then 450 lines is something else. It's implementing sort of the rules of the game. So here's sort of the input format, right? Where the character starts, walls that you can never do anything with, the end of the level. Uppercase is for monster, and for a monster that takes up more than one tile, you just use the same uppercase letter, and it all, the monster all dies at once, or gets pushed or pulled at once. Lowercase is for movable obstacles. Great, so let's look at that level that we were solving. You can see these obstacles that are 2 by 1, right? 2 by 1, and then there's also some 1 by 1 obstacles. And so we're just representing that as the same letter because, of course, those pieces have to move together. But you can't break up this bed or break up this broken table. No, it's already broken. This 2 by 1 block will move together. Then we have the tools on the ground. Right? In this case, we have the shield and the glove and the sword. And then, spike, a stool, an arrow. An arrow never starts on the ground, but once you fire the bow, it produces an arrow. And potentially a portal to teleport from one place to another. And then a move is the tool that you're using and the direction that you're using it in. So you can walk, you can sword, you can bow, you can shield, you can glove. Okay, so what is the rest of this code actually doing? So we have directions, which is just up, right, down, and left, and just some sort of utility functions for that, including sort of the backwards direction, which is useful for pulling. Right, because you're pulling a thing that is in like the opposite direction that you're moving. Anyway, so how do we represent the state? This is the most crucial thing, and I maybe haven't chosen the best representation here. Actually, I think it makes it a bit slower, but it's it's easier to think about, which is why I picked this. So we have the number of rows and columns of our grid. We have our position in the grid, and then we have just the current state of the board as just like a 2D character array, right, following this format. So that's like where the arrow comes in, and then we have which tools we picked up, right? So basically corresponding to this bottom bar. And then we have just like a bunch of utility functions here. It's like, is this square valid? Is this square a tool? Is this square a spike? Is this square a portal? Actually perform a portal move. So assuming that you're on one of the portals, teleport to the other one. Right, so find the matching portal that isn't the one that you're already on, and then move there. Is this square a stool? Is it an arrow? Is it an empty space? Is it a place that I can walk to when I'm pushing something, which is either empty or stool? Is it something I can push, which is a monster, an obstacle, a stool, a tool, or an arrow? Is it a space that I could walk to? Right, so these are all the things that you can walk to with the boots, including the exit if you kill all the monsters. Have I fired the arrow or not? How many monsters are left? Is the number of monsters left 0? This is probably the most complicated function in this whole thing, which is just to push something, which could be a stool, or an obstacle, or a monster, or a tool, or an arrow. A bunch of things are actually pushable. I guess the tricky thing here is that the obstacles and the monsters can be more than one square big. So you need to push like the whole thing. So right, we have some square that we're trying to push in some direction. Go through the rest of the grid and identify other squares that are part of that same object, right, that are represented by the same letter, which are just monsters and obstacles are the only things that are bigger. Stools are actually tricky because I'm representing, right, so monsters and obstacles, different ones I represent with different letters, but stools I just represent always with star in here. So you have to know that two adjacent stools are not, they don't get pushed together. So that's what this clause is about. So anyway, if this other tile is the same, is part of the same object, then we want to push it as well. So if you try to push it, to something that square that doesn't exist, obviously that doesn't work. Or if you try to push it to a square that's not pushable, that doesn't work. Or if you push it onto a spike, then you might kill it. And you can the only thing you can put on the spikes is monsters. I thought maybe I had a bug there, but okay, this is checking for that. You can't push like a table onto a spike, but if you push a monster onto a spike, that'll kill it. And then remove it from all the places where it used to be. And if it's a dead monster, then you don't need to replace it. But otherwise, move it to its new position. So that's pushing. That's, as I said, probably the most complicated thing. Then there's killing, like with the sword or the arrow. And again, there's a difficulty here, which is that you might kill a bigger, a 2x2 monster. So we just recursively look for the same monster in all 4 directions and recursively kill. This is a little BFS. Okay, this is actually a speed optimization. Because some of the later levels are actually pretty long and tricky, right? Like this one is like 30 moves, and if you think about it, just sort of naively, there's like 5 different tools, and you can use each of them in 4 directions. So there's 20 possibilities for each move, and it takes 30 or 40 moves to solve a level. That's like a big state space that you're exploring. And so there's sort of 2 ways to finish, to actually solve a level. One is that there's just not that many, it's like relatively short level, maybe like 20, 25 moves, and then you can just brute force it, basically. And that's what I observed, just running this sometime, through some levels, is if the level's like 20 to 25 moves, you can pretty much brute force it with this. Another way is that there's just like not that much that could happen in the level. Right? There's only like so many tools that you could have or not have, or so many monsters that you could shove around, and obstacles that you can shove around. And so if you just explore everything that could happen in the level, that's another way to find the solution. And so normalize, to help with that, this is saying, okay, well, all the monsters, I guess they have different graphics, but they're functionally the same. So like if I somehow swapped this archer and this slime position using these tools, that would be the same as the starting position, right? I haven't actually done anything. And so normalize is taking that over account. It's like renumbering all of the monsters and all of the obstacles so that they're sorted, top to bottom, left to right, so that I don't end up, exploring effectively the same state multiple times. So I've just swapped a monster and obstacle. So that's what that's doing. Lots of debug printing. So a move is just a tool in a direction, or an integer and a character. And then we have the parser. Right, so I have this text-based format, and I need to actually turn it into the state object. But because the main thing in my state object is just the text-based map, this is relatively easy. So I read in each line. If it's the starting position, then write down that that's the starting position, and the starting position is always empty. Otherwise, just copy down the character. Blank lines don't count, but non-blank lines should be part of the grid. And once I have read all the lines, we can check that all the rows are cut the same size, and now we have the starting state, which is just that many rows, that many columns, a starting position, and the map that we read in, and then we start with no tools, always. We only start with being able to walk around. So that's the parser. Okay. And then I said push was the most complicated function. It's the most complicated utility function. This is definitely the most complicated function, which is, given a state, what are the moves I can make, and what are the new states that result from those moves? Okay, so conceptually, it's like 100 lines long, like 20% of the code. Conceptually, the idea is straightforward, which is just for all the tools that I have, and for each of the 4 directions, consider using the tool in that direction. And if it actually does something to change the state, then mark that done. Okay, so for each of those possibilities, it could kill me, so consider that. If it actually does something, and if I need to renormalize. Okay, so this is the potential new state, which is currently just a copy of this state, and then there's 5 different tools, so I'm going to have bases for all of them, basically. So boots are actually surprisingly complicated. Right? The idea is you walk in some direction until you hit something. If it's a tool, then you pick it up and stop. If it's a stool, then you just stop. And if it's a spike, then you die, which means that it's not a valid move, basically. Right, so while I haven't hit something, find the next square. If I can actually move to that square, mark down if something happened. Right, if I just, I don't want to consider bouncing down here, which does nothing. That doesn't count. I need to keep track of whether or not I actually got to move. So move to the new square. If I landed on a tool, then pick up that tool. If I landed on a portal, then take the portal. If I landed on a spike, that's dead. I'm dead, so that's not going to be a valid move. If I landed on a stool, I have to stop. If I landed on an arrow, I pick up the arrow and stop. And if it's not a movable square, then I don't actually move to that square. Right? So I stop before hitting the wall, and then I stop. Okay, so that's the idea for boots. And basically, just if you actually manage to move a square, then that is a move that we should consider. Sword is actually the simplest tool. You can just kill something that's right next to you. So just look 1 square in that direction, and if it's a monster, then kill. The bow is similar to the boots, right? So you're sort of firing an arrow that moves until it gets something. You can only fight the arrow if there's not an arrow already on the ground, so check for that. And then figure out where the arrow is going to go. So it starts at our position, and then until it hits something, sort of look in that direction. Right, so we can move through empty squares. If we hit a monster, then we kill it. And the arrow lands where the monster was, and anything else, actually, the arrow just stops. So an arrow is not like boots, right? An arrow can't, if an arrow stops before it hits a stool, it stops before it hits a spike, it stops before it hits a tool, it stops before it hits a portal, and so on. So yeah, the only thing that it goes through empty squares and it kills monsters. And if we actually did something with the arrow, so it didn't just land on, if we tried to fire an arrow down from here, it wouldn't go anywhere, it would just be on our character. That doesn't count. Mark down that there, the arrow actually landed somewhere, and that's a valid move that we should consider. Then we have the shield, which is maybe the most complicated tool, because you both move and you push something. So while we haven't hit something, if we can't go out of bounds, sure. If it's something that you can push, then try pushing it, and also stop moving. Right, and that counts as moving, as like a valid move, we should consider. Otherwise, if it's an empty square, then we move through it, and otherwise we just stop. Right? If it's something that we can't push, we just hit a wall or something. Okay, so that's the shield, and then lastly we have the gloves. They're a little simpler than the shield because you can only pull something that's already adjacent to you. So there's no while loop here. Okay, so this is the square that we would to pull something. You have to move as well as the thing. So this is the square we would move to. This is the thing that we are trying to pull. To pull. And if this thing can be pushed, right? A push is the same as a pull. You're sort of pushing in the direction that you are moving. So if it's something, if the target is something that can be pushed, and the square that we're moving to is something that we can move to while we're pushing. This is a little bit that you can't push onto a. If there were a portal here, I couldn't pull this thing. Or I think a stool I could, but if there was a tool, I couldn't push onto it. Anyway, so if that thing is able to be pushed, then do that and mark down that happened, and also move me. Okay, so there's only 5 tools. Okay, so if something actually happened and I didn't kill myself by running into a spike, then this is going to be a new thing that can happen. And if I push something or killed something, then I might need to renormalize, to renumber, relabel all the monsters and the obstacles, so do that. If not, I prefer not to, it's a little expensive to go through the whole grid. So that's a little optimization there. And yeah, that's pretty much it, right? That's the main function. In comparison, the did we win function, incredibly simple. Just are we standing on the exit, which you can only get to if all the monsters are dead. This is just how many moves have you made. This is actually printing out the moves to get to the given state. And then this we sort of talk through, right? And there's some debug output to try to figure out what's going on. And also just, for the longer levels, I want to see that something's happening. So it's printing out how many states it's explored and how many moves it's made. And because it's a BFS, it's just sort of looking at all the possible sequences of different moves in order of the move length. Right, so it's trying all. Trying all 1 move options and then all 2 moves. So you can see, even looking just at the first 10,000 states that it got to, which is not that much, it already is making 23 moves. So I think that's an indication that this level is relatively small. It's pretty easy to explore basically everything you can do, and probably the normalization helps a lot on this level because there's 3 interchangeable little monsters and 3 interchangeable obstacles, and 2 other interchangeable obstacles. So normalizing should help. Yeah, so we can see, explore 10,000, 20,000. How many states did it end up exploring to solve the whole thing? So about 200,000 states. Sure. So, that would, you saw that, right? That was pretty fast. Actually, how fast is it? I'm curious. I'm going to time and find out. Okay, so it takes like 2.5 seconds to solve this level, which is definitely much better than I can do. And I think even much better than the guy who made this game can do, since we finished 11 under par, which is quite a lot. So yeah, that's about it. So I've solved every level at par or below, which I definitely could not have done without this program. So it's kind of neat that I can write some code to help me figure this game out. Which, I figured most of it out by myself. It's going to be more fun, but it was also fun to write up the code that could help me with the rest. The code still can't do like some levels that are just like pretty big and long. Right, like this level wants you to make 50 moves, which is like quite a lot, and it's relatively large open space. Lots of the pushing and pulling tools, so you can move pretty much anything anywhere, and there's like a lot of different movable things, right? And you can only kill things by hitting the spike. So this level is just a little bit too big for my code to handle. It's possible I could optimize it more and solve it, but at least in its current state, it can't do it. So this was the trickiest level in the game for me, actually. Okay, so that is all I wanted to say about that. Hopefully you found this interesting. And yeah, I recommend this game. If it was interesting to you, check it out.